All right, so let's proceed to the next thermal expansion. We have the volume thermal expansion. We're done with the linear thermal expansion. Linear thermal expansion, again, is the one-dimensional thermal expansion. And then we also have a area thermal expansion, which is the two-dimensional thermal expansion. So let's proceed to the higher expansion, what we call the volume thermal expansion. Okay, this is a three-dimensional thermal expansion. Suppose we have a cube here, cube. Right, so that is the cube with initial edge of L of O. L of O is the length of the edge at initial temperature, or T of O. Okay, so let's assume that this cube will expand in all direction, because remember this term in area thermal expansion, the isotropic expansion. Okay, the isotropic expansion is the expansion in all the object will expand in all directions as increase of temperature. All right, so we have L of O again as the initial edge of the cube. So the initial volume V of O will be L of O cube. All right, now after increasing the temperature of this cube, so there is a change of L of O uh, for every change of length for every edge of this cube, delta L. Okay, so this is the change of length. And delta L in linear thermal expansion is alpha times the initial length times the change of temperature delta T. Now what will be the volume at the final temperature, right? Or the final volume. Since initially it's the length of the edge is L of O, and after increasing the temperature, there is a change of delta L, or there is delta L as increase of temperature. So the final volume V will be the initial L of O, initial length edge of this cube, plus the change of length of edge of this cube. So you need to let this binomial uh, raised to the power of 3 or cube. Right. So let us expand this, the L of O plus delta L. Uh, what is the cube of a binomial A times B cube? That will be A cube plus 3A squared B plus 3AB squared plus B cube. Right? Because remember this in your basic algebra. The cube of a binomial means a expression with two terms, algebraic expression with two terms. So it's A plus B. So A plus B cube is A cube plus 3A squared B plus 3AB squared plus B cube. So here, we're going to compare L of O plus delta L to A plus B. L of O is A and delta L is B. So what will be L of O plus delta L cube? Since we have A cube here, then we have L of O cube plus 3A squared. So 3A is L of O, and so we have A squared, then that is L of O squared times B here is delta L, so this is delta L plus 3A, what is A is L of O plus B squared, that's delta L squared, all right, plus B cube. B here is delta L, then we have delta L cube, right? So let us simplify. That's L of O cube Okay, that's L of O cube. And plus 3 L of O squared. All right. Oh, come on. Right. So you have 3L of O squared. And what is delta L? Delta L is alpha. Alpha here is the coefficient of linear thermal expansion. So let us substitute delta L by this one. Alpha L of O delta T. And that is alpha L of O delta T plus 3 L of O. Um, so let us again replace delta L by alpha L of O delta T. And we'll need to raise this to the second power. We have alpha L of O delta T squared plus delta L cube is this one. Again, let us replace delta L by alpha L of O delta T. So this is alpha L of O delta T cube, right? So what is this L of O cube? Let's go back. L of O cube is the initial volume of this cube. So we'll replace L of O cube by V of O plus 3 times L of O squared times L of O. That's L of O cube. Then alpha delta T plus, right? This is 3 L of, this is L of O times L of O squared, since we raised this to the power of 2. That's L of O cube alpha squared delta T squared plus this one, that's alpha cube plus, no, times L of O cube delta T. All right. So again, what is L of cube here? That is the initial volume of the cube. So that will be 3 V of O, right? L of O cube is V of O. Now alpha delta T plus 3 V of O alpha squared delta T squared. So plus alpha L of O cube is just the initial volume times delta T, right? Now, if we're going to square, the coefficient of linear thermal expansion, at the alpha square, that's approximately equal to 0. How much more if we're going to raise that, the coefficient of linear thermal expansion to the third power, or alpha cube, it will be again approximately equal to 0. So you can neglect this. You have alpha squared, that's then multiply by 3 V of O delta T, that's approximately equal to 0. And then I forgot to put cube here. Now the alpha cube, that's again approximately equal to 0. Multiply by this V of O delta T, then so we can neglect that one. We don't include that one. These two are approximately equal to 0. So let us consider these two terms only. V of O plus 3V of O alpha delta T. Right? So that's the final volume. Final volume is V of O plus 3V of O alpha delta T. So let us factor this. You have V of O times 1 plus 3 alpha delta T. Alright, 3 alpha here, this one, 3 alpha. I'll make that as beta. 3 alpha equals beta, and that is what we call the volume coefficient of coefficient of volume thermal expansion. Coefficient of volume thermal expansion. Right? So that's the 3 times of alpha is beta, and that is coefficient of volume thermal expansion. All right. So again, we consider this expansion as isotropic expansion. So it means 3 alpha here, the 3 alpha, which is equal to beta, is only good if the expansion is isotropic, or the material that expands will expand at all directions. Okay, so that's 3 alpha equals beta. So the final volume, let me erase this because since this is a final volume, not a... Okay, so the final volume now is V of O times 1 plus, now since we have 3 alpha times delta T, the change of temperature, then we replace 3 alpha by beta. This is now beta delta T. Right? So V here is the volume at the final temperature TF. Okay, and beta, you know already what beta is. That is the coefficient of volume thermal expansion, and then delta T is the change of temperature. Okay. So by looking at this equation, V equals V of O plus 1 plus beta delta T. Going to multiply V of O plus 1, we have V of O plus, okay, distribute V of O plus beta times beta delta T. V of O here is this the initial volume of that material. Okay. Now the final volume must be initial volume plus the change of the volume. By looking at this equation, we can see that this one is delta V, the change of volume. So therefore, the change of volume here is the initial volume times the coefficient of volume thermal expansion, which is beta, times delta D. Right? Okay, so that is for volume thermal expansion. Okay, delta V here is the change of volume. Again, V of O is the initial volume. Beta, which is 3 times the coefficient of linear thermal expansion, and delta T is the change of temperature. It should be final minus initial. Now, as increase of temperature, there is increase of size. That's expansion. Now, if there is decrease of temperature, there is decrease of size, and that is the opposite of expansion. We have contraction. All right. So we will solve a sample problem involving volume thermal expansion. So let us solve problem involving volume thermal expansion. So the problem goes this way. A copper cylinder is initially 20 degrees Celsius. At what temperature will its volume be 0.25% larger than it is at 20 degrees Celsius? All right. So that's 0.25% larger than its initial volume. Initial temperature is 20 degrees Celsius. By analyzing the problem, the change of volume must be 25% of the initial volume, or that's 0.00025. of the initial volume. Is 0. Okay, that's 0.0025 of the initial volume. Now we know that delta V is the initial volume V, beta delta T. All right, and then the beta here is 3 times alpha. Right, and then what type of material is this? The cylinder is made of copper, and we know the alpha of copper, or the coefficient of linear thermal expansion of copper, is 17 times 10 to negative 6. So we have beta is 3 times the alpha of copper, which is 17 times 10 to negative 6. Okay. So what is 17 times 10 to negative 6 multiplied by 3? So beta is multiplied. You can use your calculator to double check if it is correct. That's 5.1 times 10 to the power of negative 5. Right, so we can now solve. What is asked here is the final temperature. So at what temperature the volume of the copper cylinder is 0.25% larger than when it is at initial volume. Then we have V, delta V is equal to initial times beta delta T. Right. What's the change of volume here? That's 0.00025 of the initial volume. 0.0025 of its initial volume, so equals initial volume beta delta T, or delta T equals 0.025025 of the initial volume divided by the initial volume times what is beta, that's 5.1 times 10 to negative 5. Right, again this is beta per Celsius degree, right? Not degree Celsius, since we focus on the change of temperature. Okay, so we can cancel the initial volume, V of O. Let us divide. Use your calculator to double check if it is correct. 0.0025 divided by 5.1 times 10 to negative 5. This is the delta T here. Delta T is 4.9. It's 4.9. Come on. 4.9 Celsius degree. Alright. So this is not what is asked on the problem. The problem is asking for the final temperature. So we know that the change of temperature should be final temperature minus initial temperature. So the final temperature here will be the change of temperature plus the initial. Right. So the final temperature will be the sum of the change of temperature, is 4.9 Celsius degree, plus initially the cylinder is at 20 degrees Celsius. We can still add, though they don't have the same unit. They are all in temperature, so Celsius degree again is just indicating that this is a change of temperature. So it means at 24, not 4.9 plus 20, that's 24.9 degrees Celsius. Okay, that's the final temperature. So this is what is asked in the problem. At what temperature the copper is 0.25% larger than when that copper is at initial temperature, when it is at 20 degrees Celsius. right? So this is the temperature where the volume of the copper cylinder is 0.25% larger than its initial volume. Right? Let us solve another problem involving volume thermal expansion. And the second problem goes this way. Suppose your 60-liter steel gasoline tank is full of gas. So both of the tank and the gasoline have the same temperature of 10 degrees Celsius. So they are initially at 10 degrees Celsius. How much gasoline has spilled by the time they warm to 35 degrees Celsius? All right. So I have here the alpha of steel, which is 11 times 10 to negative 6. The beta of gasoline is 9.6 times 10 to negative 4 per Celsius degree, right? So when we analyze this problem, initially, well, the tank and the gasoline, the tank is made of steel, so that's why we have the alpha of steel. So initially, the tank and the gasoline is at 60 liters at 10 degrees Celsius, right? Now, what is asked here is the amount of gasoline that will spill out when both the tank, the gasoline tank, the steel tank, and the gasoline are warm up to 35 degrees Celsius. The change of temperature is 35 degrees Celsius minus 10 degrees Celsius, right? So we have the change of temperature equals 25 degrees, since this is a change of temperature, 25 Celsius degree. All right. So if we're going to compare the expansion, the volume expansion of the steel tank and gasoline, steel tank is a solid material, the gasoline is a liquid material. So it's expected that the gasoline will expand more faster compared to the solid material. So the amount of the gasoline that is spill out in the tank will be, of course, the change volume of the gasoline G minus the change volume of the steel tank. That is the amount of gasoline that will spill out. Spill out of the tank, right? So the change, again, the change of volume of the gasoline minus the change in volume of the steel will be the amount of gasoline that will spill out. All right. Now, both of them are subjected to a temperature from 10 to 35 degrees Celsius. So we have the change of temperature of 25 degrees Celsius. Right. Oops, where are you? Okay, so let us solve. Now, what's the change of volume of the gasoline? That is the change volume of gasoline will be the beta of gasoline, the initial volume of the gasoline, delta T, right? And then what's beta of gasoline is 9.6 times 10 to negative 4 per Celsius degree, multiplied by the initial volume, which is 60 liters, times the change of temperature, which is 25 Celsius degree. Okay, use your calculator to double check. That's 9.6 to negative 4 times 60 liters times 25. So the amount of um, change volume of gasoline is approximately 1.44. Since we have liter as the unit of volume, by the way, we can cancel Celsius degree here. So what is left is liter. So this is the change volume of the gasoline. The change volume of the steel tank, sub S meaning steel tank, will be beta of the steel tank, initial volume of the steel tank times delta T. Right. But what is beta of the gasoline? Steel tank, I mean. Okay, let's solve first for the beta. Beta is 3 times alpha. The alpha of the steel tank is 11 times 10 to negative 6 per Celsius degree. We have beta equals 33 times 10 to negative 6. Right, that's for beta. Okay, then we can now solve for the change volume of the steel tank, and that is 33 times 10 to negative 6 per Celsius degree multiplied by what's the initial volume of the steel tank? That's 60 liters times the change of temperature. Both the gasoline and the steel tank are subjected to this change of temperature, 25 Celsius degree. So it's 25 Celsius degree. Degree. All right. So let us solve. You can use your calculator. That is 0.0495. So both the steel tank and the gasoline are subjected to this change in temperature, 25 Celsius degree. The gasoline expands more compared to the steel tank. So we can solve for the volume that spill out. The volume SP, meaning the gasoline that spill out, will be equal to the changed volume of the gasoline minus the changed volume of the steel tank. We have 1.44 liters, that is the amount of change of volume of the gasoline, minus delta V of S, that's the change volume of the steel tank, which is 0.0495 liters. So the amount of volume that spill out when both are warmed up to 35 degrees Celsius would be, that's 1.44 minus 0.0095. Okay, that's 1.4305 liters. 1.4. I'm using calculator to double check. 305 liters. Right. So that's the amount of gasoline that spill out when it was warm up to 35 degrees Celsius. So that's problem number 2.